All right, so y'all did awesome at conquering magnetic fields and just the introduction to that. So let's look at your warm-up. Illustrate the magnetic field lines surrounding the bar magnet. We know they go out of north, right, and into the south. And so that means they always end up pointing back around. Remember we said they form full circles as they go back around. So you should have drawn your arrows going out of the north and into the south. All of the field domains and which direction will increase in size if it was placed above this magnet. So say we put this little paper clip down here and we're going to see all of its little domains. So if we zoom in, we see all the domains pointing all random different directions, right? Might go down, might go back. That's what our magnet or our paper clip originally looks like before we place it beside the magnet. As I move up here and get beside the magnet, what happens to all these little field or the domains within my paper clip? Everything that is lined up with the field lines of this magnet are going to grow, and it's going to magnetize this paper clip. All right, so that means everything pointing in this direction. So all of my arrows pointing to the left are going to grow in size, and they're going to swell, creating that overall net field. All right, now that everything has swelled and kind of pushed down and shrunk everything else pointing the other way, it is now magnetized. All right, so if this paper clip were stuck in the magnet and then I added another paper clip, right, this paper clip's now magnetic and it could stick to another paper clip. So if you've seen before, if somebody takes a magnet and dips it into like a bowl of paper clips, it doesn't always just bring up one paper clip. Sometimes paper clips are hanging onto other paper clips, because now that this object is magnetized, it can now pick up another ferromagnet and attach to it, right? Because now it is magnetized. It is ferromagnetic materials are only magnetized when they're placed beside a magnetic material. All right? So, obviously we've seen a bunch of different ways that energy and magnetism are alike. All right, so what is that missing link? Before 1820, scientists thought, you know what, electricity and magnetism, we think they're related, but we don't know how, right? There's no proof of it. So think of some similarities between those two. All right, they both have poles, whether it's to be a positive and a negative end, or a north and a south end, right? Also, in both of them, opposites attract, like charges repel. They both create fields. You have your electrical fields, you have your magnetic fields. All right, the closer you are to the source of that field, so the closer you are towards that object, the stronger the force. The more you move away, the weaker that force gets. All right, so a lot of similarities that we see in between the two. So where do you think we finally found some answers? In 1820, this Danish physicist, he discovered the connection. He took a compass and he ran it over a wire where there was some electrical current going through. All right, and as a result, the needle in the compass deflected. It started moving, right? We know that typically compasses only move and point in different directions if I'm turning and facing different directions, right? But if I'm holding this compass and I'm still facing the same direction and I cross over a wire and it starts to flicker, then that means something's impacting it, right? Something is creating a magnetic field. So what is that? A current-carrying wire creates a magnetic field. All right? So electromagnetism is what we call this. The electromagnetic force is that attractive or repulsive force between the electrical charges and magnets. All right? So therefore, charges and magnets, they have some forces that exist between the two of them, and they impact each other. So currents create magnetism. A current-carrying wire, think about your power lines, right? These wires carry current. Or, whatever you may have plugged in. If you plug in your cell phone, that wire carries a current, all right? So what do those fields look like? Magnetic fields circle around the wire. So here's our wire, and that field circles it. It goes in circles around your wire. So this is your electric current, and this is your magnetic field circling the electricity. All right, so how do we determine which direction the magnetic field goes in? There's a bunch of different possibilities. Does it turn left? Does it turn right? How does it circle around it? All right, so it goes if we take our thumb, we have our right hand rule. All right, always use your right hand. Also, as you're going to get it twisted around, you're going to point your thumb in the direction of the current. So here's my wire, and it shows that the current is flowing this way. All right, flowing towards the object that I'm trying to supply energy to. If I put my thumb in the direction of that current, my fingers represent the direction that it's wrapping around. So put your hand up and put your thumb up. If you look, imagine this circle right here is the direction of your magnetism. Follow your arm, and which way does it curl around? It curls around to the front. All right, so if our current is flowing upward, it's flowing around in this direction. All right, so pretty easy trick. Don't overthink it and get confused with it. All right, thumb up, and then whichever way your fingers curl is the direction of that magnetic field around your wire. All right, so what factors do you think affect the strength of that magnetic field that surrounds your wire or your current? The stronger the current, the stronger the magnetic field, right? So as we increase the current, we increase the flow of what's going through. Think of it as it's circling around, right? But as I keep pumping more and more and more, think of a faster paced river, right? We compared our electrical current to like the current of a river, all right? The faster our river flows, imagine this is like a little turnboat around, the little water mills, all right? Imagine this is a little water mill going around it. The stronger that flow of current, the stronger that magnetic field gets. All right, so you're gonna feel an increase in push or pull of that magnetic field. It's going to have a greater effect. If I were to take a compass over it, you're going to see it flicker a lot more the greater the current is. All right, closer to the wire. We know that everything that we've talked about these last few units gets stronger the closer we get to the source. All right, so the closer I get to the source or the wire, the stronger my magnetic field is. As I back away from the wire, I'm not going to feel as much of a force or an impact from that magnetic field. All right. But as the current increases and the closer I get to that wire, my magnetic field is also going to increase. All right, so taking this a step farther, and we can create a magnet known as an electromagnet using solenoids and electrical current. All right, so a solenoid is a wire that's simply wrapped into a coil. All right, so if you notice, it's wrapped around in a simple little coil right here. So let me grab something, and I'll be right back so we can kind of look at this. All right. So right here I have a wire. If y'all can see, it's an electrical wire wrapped into a coil. All right, so I took it and I wrapped it around in a circle. This right here is a solenoid, a wire wrapped into a coil. In this coil, all right, the magnetic field inside is stronger. All right, if I were to measure it outside versus inside, I have a stronger magnetic field. All right. If I look, once I add an iron core to my solenoid. So here's my solenoid, here's my iron core. I have an iron nail. I put that in the center. I've now made my solenoid really strong. All right, so now I've created an electromagnet. A solenoid, right here, our coil with an iron core is an electromagnet. All right, so I've increased the strength. All right, so wrapping a wire coil around a current carrying iron, I said that way mixed up. Wrapping a coil, this wire, imagine I had it plugged into a battery. All right, wrapping it, carrying current around an iron core creates an electromagnet. So here's my little wire wrapped around, and let's say here's our battery. So now it's carrying a current around that iron core. I now have a magnet. All right, so the solenoid of the solenoid's magnetic field magnetizes this iron core, or my nail, right? Because this is a ferromagnet. It can be affected by those magnetic fields. All right, so the field inside of that solenoid with the iron core is 1,000 times stronger than without the iron core. So this alone, if I were to connect this back to my little battery up here, all right, This alone has a very, very, very weak magnetic field. But once I add in my iron core, if I attach it to a battery, I'm probably going to pick up some paper clips, some different things that are ferromagnetic objects. They're going to now be attracted to my iron core. All right, you're going to do a lab with this also later on in your unit. We're going to talk about building ferromagnetics and what increases their strength. So, properties of electromagnets. All right. Electromagnets are temporary magnets because the magnetic field is only present when current is flowing. If I disconnect my battery and I take it away, is this a magnet anymore? No, it's not going to pick anything up. It's nothing more. We notice here's my paper clip. All right, it's nothing more than a nail with wire around it. But if I were to connect these two ends to a battery, it's now going to pick up that magnet. Let me go see if I can grab a battery and show you all. So I've got my battery now, and I'm going to show you all how this works. All right, so here's my nail with my wire around it. If you look, it doesn't pick up this paper clip, right? It's nothing more than a solenoid with an iron core. But when I add that current to it and I allow current to flow through, so here's my battery, and hopefully my battery's not dead so that this will work. All right, when I add my battery to it, watch what happens. I've now picked up my paper clip. All right, so I just created an electromagnet. All right, if I disconnect the current and I take it away from the battery, look what happens, right? It no longer picks it up. It does take a second, so why, probably you're wondering, why does it stick there for a second after my current is disconnected? All right, so when we talk about in ferromagnets, the domains rearrange. All right, so it takes a second for those domains to even back out, spread back out the way they were, and kind of get disorganized again. Right now, all of our domains are in the same direction. It's a ferromagnetic. It now has aligned domains, a magnetic domain. But when I disconnect it, it takes a second for it to realign and discombobulate again, basically for all your domains to go in different directions. So that right there is a ferromagnet. If you notice, if I take the iron core out, right, this makes it 1,000 times stronger. So if I take my iron core out and I only have my coil, all right, and my battery, it does not pick anything up anymore, all right? You have to have this iron core. It's getting really hot. So when you all do this lab, please be careful. Don't burn yourselves. The batteries will get a little bit hot. All right, now when I add that iron core, look how much stronger it is. So this right here is an electromagnet made by a current flowing through a wrapped coil, which we call a solenoid, that has a iron core in the middle of it. So add that iron core to your solenoid and you've created an electromagnet. All right, so you'll do a lab and you'll talk about the difference and how many batteries you have tells you how many paper clips you can pick up. The more batteries you have, the more paper clips you'll grab. All right, so one way that we can increase the strength of our electromagnet is adding more turns of the wire. So if I put a whole little like pile of paper clips down here, you would see quite a few of them attached to this electromagnet. All right, if I were to unwrap this coil, all right, which I'm not going to do right now because it takes a while to wrap it back up. If I were to unwrap this and say it was only wrapped around like twice, it's not going to be very strong, right? Because we don't have much of a current wrapped around to create a flow. All right, so adding more turns makes it stronger. All right, or we can increase the current. So what did I say? Add some more batteries. If I add some more batteries, I've got greater potential difference, right? So I'm going to have a greater pull of current through my wire. The greater the current, hence adding more batteries, all right, and adding more turns is going to make your electromagnet stronger. So electric motors, how do electric motors work? In your vehicles, maybe in like the heater that you have in the winter, those electric motors use magnets and solenoids in order to change electrical energy into mechanical energy, right? So we're going to look at an example of that, but fans, blenders, vacuum cleaners, all kinds of different things that operate off of electricity, right? How do we take that electricity that comes out of the power line and all of a sudden make something turn, which is our mechanical energy? So when we look at it here, the current flows into the coil, creating a magnetic field. All right, so here's our current. It flows in this coil, creates that magnetic field. This is allowed to spin. Right here we have a permanent magnet. It never moves. So as that current flows through your coil, this right here is going to end up spinning, right, to try and balance itself out between the north and the south of that permanent magnet. And as it continues to spin, therefore your motor starts moving, right? So literally a motor is nothing more than the spin that results from magnetic fields, all right? Magnetic fields that result from the current flowing through. All right, so current flows through, creates that additional magnetic field right here, and it begins to spin. Motors need to spin to operate, right? If you were to break down any object at its core, there's something in the middle spinning that's doing all of the work, whether it's a vacuum cleaner, a heater, projector, that's got little things in it that are spinning as a result of that magnetism. So motors and generators, they use electrical current to power electromagnets to turn that shaft. All right, so any type of motor, generator, anything that supplies you with energy, so it ends up doing work for you, all right, is the result of a magnetic field turning a shaft as a result from that electrical current. So think about this image right here. Current goes in, this spins because it has now created a magnetic field that's trying to balance out between this permanent magnet there at the end. All right, so what happens if you reverse the process? Imagine you crank it, there's no energy supplied, right? But I crank it by hand and I'm turning that magnet in here. So now let's take this out, and over here I'm cranking it and I'm turning it, creating that flux in magnetic field. What do you think I create? If the current created turning, what do you think turning creates? Current. All right, so that's what generators do. All right, so the motor produces an electrical current. It now has become an electrical generator. So right here I'm cranking it and I'm turning that electromagnet inside of my permanent magnet, and I have created current. Guess what? That's what big power plants are. They're one great big cranking, all right? They're cranking, and as a result producing electricity. So that is exactly what a power plant is a great big generator. So generators transform that mechanical energy, if you see right here, mechanical energy to electrical energy, going back the other way. Instead of using energy to make something turn, we're turning something to create electrical energy. All right, so right here, if you can see, they're cranking that knob, and as that flux of magnetic fields goes, it comes through and it goes into your light bulb and lights it up. What does it take to light up that light bulb? Electrical energy. All right, so current is produced in the coil as it turns between the poles of the magnet. So what do motors and generators have in common? They're basically the opposites of each other. Motors use those electrical currents to generate magnetic fields, all right? Vice versa, generators make those changing magnetic fields generate electric currents, all right? So motors, think about when we plug something into the wall, it makes the motor run, so you're taking that electrical energy and turning it into mechanical energy. Vice versa, generators, right? Think about our power plants. They generate electricity. How? They use that changing flux of magnetic fields and that mechanical energy to generate electrical current. So they're just the opposites of each other. So take a break. Take a few seconds, take a little mind break, and then we'll move on. I feel like I've kind of thrown a lot at you at once. So take a second, look over your notes, just take a breather, and then we'll talk about induction, magnetic flux, and things like that. All right? Awesome job.